Welcome, geometry scholars of SAS. Congratulations on finishing your quiz, and welcome to the next post-quiz video, maybe one of the last ones of the year. All right, so this one's about volume and surface area of a sphere, including this idea of Cavalieri's principle. Here on the front page is all the stuff we're going to talk about, in case you want to come back and say, what was that about? Or if you want to stop now and leave while you can. Anyway, you have a worksheet that goes along with this and has this stuff at the top. Okay, so first thing, spheres you've probably seen before. They look like, a ball. And just like circles and everything else we've studied this year, they come along with things you're supposed to know about how to measure them. And the first thing, from the center point to any point on the sphere, you find this thing called a radius. And just like circles, remember a circle was defined as every point in the plane that is a given distance away from a given center. This is the same kind of idea, but now we're in 3D. So the sphere is every point in space that's a given distance, which we call radius, away from the center. And just like in circles, not only does the sphere have a radius, but it has a diameter, and the diameter is just 2r, so that's no big deal. The idea of great circle is a little different. Great circle, we could draw a circle around the sphere, kind of like an equator, and that's what they call a great circle. The radius of the great circle would be the same as the radius of the sphere. Another way to think about that, like you can see down here, is if you chop the sphere with a plane so that it goes through the center of the circle that is the intersection of that sphere with that plane, we would call a great circle. Here's another picture of that up here, where we've got this slice. It looks like a piece of paper kind of hanging in the middle of the sphere. If it goes right through the fattest part of the sphere, the circle that you could make on that piece of paper is called a great circle. Anything else is called a small circle. I've got a better picture of that here. Here's a sphere with, it's a little more dynamic. It's got these slices made in it. Try not to worry about that green thing. This is actually from a way more complicated demonstration. But I'm wiggling this thing up and down. This sphere has been cut by a plane right here through the center, and that circle that it's making on the sphere, I'm wiggling it around. Yeah, again, ignore the green triangle. It's called a great circle. These circles are called small circles, and on this you can actually move it. So right there, I've got sort of the great circle hits itself. If you slice it any smaller, you're going to get these, or a slice that does not go through the center, it's going to be smaller. And there's going to be problems where we do this, like we have a bowl of water and the water level is going down and the surface area of the water is such and such. You're trying to find the radius of that and the exposed water, or how much water is in there, that kind of stuff. So that's coming. And of course, they don't have to be vertical. They can be sideways and that kind of stuff. And the slices will do that as they change. I bring this up now because Cavalieri's principle has a lot to do with this, and we're going to talk about that in a second. One last term you might see associated with the term sphere is this idea of hemisphere. We had semicircles for half a circle. For spheres, for whatever reason, they don't say semi, they say hemi. So a hemisphere is exactly that. All right, so let me just go ahead and hit you with two formulas you're going to need for this section. One is about surface area of a sphere. There's the formula. I'm just going to give it to you first, and we'll talk about why later. And the volume of a sphere. There it is. Now this looks big and nasty, but it actually is not too bad once you get into it. The only dimension in that we really care about, that we need to know about the sphere in order to know how big it is, both in terms of area and surface area and volume, is radius, of course. So once you have radius, you just plug it into these formulas and you're good to go. All right, so let's actually do some problems. Okay, so this would be the most straight ahead problem you got, where you get the radius and it asks you for those two different things. Let's find, oh, sorry, I lost my pen here. Let's find surface area and let's find volume. Remember, the formula for surface area was just 4 pi r squared, and the formula for volume was 4/3 pi r cubed. In the process, we'll probably have to talk about how you do some of this stuff on the calculator. All right, so the surface area, I use surface area, the book uses total area, it's the same thing. Surface area of the sphere is 4 pi times that radius squared. That radius squared is 25. 25 times 4 is pretty easy. That's 100 pi. If I wanted approximate, I would ask for that on the calculator. It's probably 314 or so. And the volume, can I squeeze that over here? The volume is 4/3 times pi times that radius cubed. Well, that radius cubed we haven't done in a while. We haven't cubed any numbers, but that's 5 times 5 times 5. That's just 125. 125 times 4/3. Yeah, that's not anything I care to do by hand, so I'm going to do that on here. 4/3. You've seen those before. It's control divided for that fraction. Pi's under here. What? What just happened there? Oh, wrong button. It's too small. Pi, thank you, times, well, I could do 5 cubed this way if I was really lazy. 5 exponent. Remember that exponent button is. We're going to need it in a second. 500 pi over 3. You all right with that? Hope so, because that's the right answer. All right, 500 pi over 3. Anxious as to why these work yet? Okay, we'll get there. Here's one more, though, before we do. Actually, we'll do these two more before we go there. Circumference of this great circle is 59.7. Circumference of that great circle is 59.7. Remember, that's 2 pi r. So from this, we can find r pretty quick. And from that, then we can do everything we need to do. So 59.7 was 2 pi r. So I take 59.7 and divide it by 2 pi. I bet this is probably a rounded value. I haven't done this problem before. It's probably supposed to be nice. It's probably supposed to be 9.5. Let's just say that's supposed to be 9.5. Whoops, that's not what I meant to say. From this, I can figure out that r is 9.5. All right, so if r is 9.5, I can do exactly the same thing as before. And man, I'm going to run out of room. I'll tell you that right now. Surface area is 4 pi times that radius squared. And when I go to put that in the calculator, I could call this 9.5. If I want to preserve accuracy, I might as well operate with that number. So I'll go control answer, and I can use that same number in there. So let's say it's not really 9.5. Let's say it's really 9.5, blah, 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 blah. Then my surface area is 1134.49. And again, that's rounded because I decimalized my pi in the process. Volume, 4/3 pi approximately 9.5 cubed. Let's see what that is on the calculator. So I do all that same stuff. Actually, I'll do this. I'll show you what I did here. So pretend that wasn't there. I get to this point, I want to grab this number again. I can actually just arrow up to get to that number, hit enter, and it'll go in there. Oh, I forgot it. I didn't get a times in there. Arrow back, hit a times, and let's cube that. Again, preserving accuracy. And I get a number more like 30, and it gives me 2 decimals, which is all you need for the answers on our test. 3593. Oh, again, approximately, because the pi has now been decimalized in there. 0.12. Okay, great. Last one, hemisphere. Diameter 15 needs to be painted. You know what? I'm just going to start doing this if I see a diameter 15. Determine its surface area. Okay, surface area for this thing, I'm going to need the whole roof plus the circle. That's what that is. So let's just do this. Roof is going to be half of the surface area of a sphere. So that's going to be 2 pi r squared. And then the base is actually just 1 pi r squared. So you know what? I'm going to cheat and just say this is 3 pi r squared. That doesn't always get to happen. All right, so this is going to be 3 times pi times r squared, calculator. All right, and that is, oh, wow, 530.14. Okay, great. Okay, so if you weren't frustrated yet, maybe you are now, about where on earth did they get 4/3 pi r cubed, what is this sorcery, and where does 4 pi r squared come from? Actually, that was developed centuries ago, and it was, one of the ways we can show you is based on a principle that was developed by this guy named Cavalieri. Cavalieri had this idea that if you had 2 solids, and you could find the volume of one, but you couldn't find the volume of another. Like this one's really kind of crazy. Actually, both these are kind of crazy. These are, this is just for an example, but these are some crazy things you're going to learn in calculus someday. Was about, well, if the 2 solids have the same base area and they have the same height, and at any point where you decide to slice them, at any height where you draw or you cut through here with a plane like they did here, and you find the area of that little thing, you find the area of that little thing, if those are always the same for the entire stack, imagine this is like a stack of Post-it notes that change size. This is also a stack of Post-it notes that change size. But if at any level, if the same level, if the Post-it notes are the same size, then the solids have the same volume. Or if you're like filling it with water, you fill them up so that they kind of rise at the same time. You stop, find the surface area of the water. If they're always the same surface area of water, then you're always going to have the same volume. The model that they use for showing how that is relevant for sphere volume looks like this. They take a hemisphere and they compare it to this thing that I've heard called an arena before. So you make a hemisphere, and of course the hemisphere, just all you have to worry about on hemisphere is the radius. You get that figured out. The height of this thing would be the same as the radius. You think about the radius in here, whatever it is. Remember, the radius is the same. The radius to this is the same to any point on the sphere, so that would be the same. And you construct this thing, which is a cylinder that has to have the same base area for this Cavalieri principle to work. So that has to be the same. The height of it has to be the same as that. And then from that, I don't know if you can tell here, but what they've done is they've drilled out this cone. And the cone has, the whole top of the cylinder has been removed by this cone, so that's the base of the subtracted cone, and the point of the vertex of that subtracted cone is right in the middle of the base of that cylinder. So that's called an arena. It kind of looks like an arena. It has a really small kind of one point size field at the bottom of that stadium, but it's kind of like a funnel inside a can. So here's a picture of that. Here's the two things. If I start slicing down from the top, you start to see these red areas. And the claim here is that the red area is the same no matter what height. So the height of the slice is always the same. At the top of the hole, the very top slice I make, the very top post-it note, has an area of 0 because it's a point on the sphere and it's a sharp ring on the top of this. It's hard to tell that there's a hole in this, but there is. That arena has been, this cone has been chopped out. You can barely tell here. But as I slice down, you can start to see. If I slice that, of course, I'm going to slice the top few rows of seats out of that arena, and I'm going to have this flat kind of running track, and I'm going to have what's called a small circle section of the sphere. So, yeah, we can actually show. It takes some not so fancy trig. It's just really some Pythagorean theorem, really, to show that the area of this thing, and I'll leave that for class if you want to ask. Or just, stop by any time during break to my room. I'd love to talk about this stuff. So come over, and I'll tell you why this circle has to have this red ring, which is big circle minus little circle, has to have the same area as this one circle for any height we can imagine. Think about that as it goes down. The hole's getting smaller because the cone is getting towards its vertex. And when we get to the very bottom, they're going to be exactly the same. We have the base of each thing. And any height where you slice it, they're going to be the same. This is kind of a fun thing to play with. Okay. This might be easier to see. This is a different website. They've made them upside down here, but at any height, that space between the cone and the cylinder, that ring, that post-it note that's it's like a donut, like a flat donut, that's going to have the same area as the exposed surface. Or think about like filling this up with water. Those two surface areas of the top of the water are going to have to be the same. Well, once you believe that those are all the same, think about what the volume of this thing is. The volume of this thing is going to be the volume of the cylinder, which is pi r squared times the height of that, minus the volume of the cone, which is 1/3 of the same thing, pi r squared times r. You notice how these terms are all the same. What we really have here is 2/3 pi r cubed. And guess what? That's the volume of a hemisphere. So the entire sphere is going to be 4/3 pi r cubed. So really this volume of a sphere is completely related to the volume of a cone, and we started seeing 1/3 when we were doing that. Now the formula for surface area of a sphere is completely different, and it's actually derived from the volume. If you know the volume formula first, there's a way to hack up a sphere and think about the surface in terms of the volume, and you can get it that way. I'm not going to have enough time to show it in this video, but again, stop by. I'd love to talk about it. But here's one more example of a Cavalieri principle that works. We have here a sphere compared to a tetrahedron. Actually, I don't think it's a perfect tetrahedron, but it's a triangle pyramid nonetheless. But you notice as we change the water level in this, oh, please work for me. Yeah. These, you can actually show that exposed rectangle, that rectangle thing over here, if you know the dimensions of this correctly, is always equal to the circle that's based here. So you can actually find it as a pyramid compared to a sphere to get the volume of a sphere too. Very cool stuff. And there's other ones all throughout other types of geometry you'll see. This is the first one that's kind of cool. All right, now so all that's over, I have just a very short amount of time to go through these problems, which are kind of the backwards problems where they give you something like surface area and you have to find diameter. I'm going to probably have to pause and click through this pretty fast. You might have to pause the video to follow along just to see what was happening here. First of all, the 300 is the surface area, and I know the surface area comes from 4 pi r squared, so I can solve that for r. So I solve that for r, and I get 75 over pi, then take the square root. But it wants diameter, so guess what? Diameter is just 2 of those. Okay, and this is the exact form. If you want decimals, be my guest using the calculator. All right, here we have the volume of 7238.23. So again, that equals the volume. We solve that for r cubed first. And we get some horrible number. Sometimes this will have to be exact, but sometimes it could be approximate. Let's do approximate for this one. And wow, the calculator even rounds it exactly to, or it rounds it to 1728. Now the first thing we have to do here, we haven't done a long, or maybe ever, is find the cube root of 1728. That's the number that times itself is that. And the way to enter that is go control exponent, put a 3 in there, and then put your 1728 in here, and it'll tell you what it is. Okay, that's it. I'm out of time. Radius is 12. I leave it to you to find surface area, but once you have radius, it's easy, 4 pi r squared. See you in class.